Yes. So until now, we saw the advantage of oversampling, but not just oversampling, but then we need to shape the quantized signal using a digital low-pass filter. So we saw all the maths behind that, and we analyzed it qualitatively and as well as quantitatively. So we said that we will see that using oversampling we can make a smaller bit quantizer look like a higher resolution quantizer. So what basically we tried to derive was, so basically we had a sequence which was let's say a sinusoidal. So we have a sequence at the input of the quantizer, and the quantizer will give some sort of output, and that output, so we analyze the error, right? So that output has the difference between that quantized output and the input signal is basically the error, and this quantizer, so this quantizer can be realized as a source along with a noise. So then that noise, we need that noise as minimal as possible. So then what we did was we filtered this quantized signal and we got xf, which near about resembles to xn, resulting in a source with a minimal noise. So the noise with the source was significantly reduced by shaping, and in previous video we said that the error between xf, which is a filtered quantized sequence, and xn is much smaller than the error between xq and xn. So in order to plot these error quantities, we pass xn through a same filter. So we need to plot it mathematically. So just for the mathematical sake, we have this sequence. So basically we have uh, this where we can get xq minus xn, which is delta squared by 12. And then we are filtering xq, right? So basically getting to get this kind of, like, if we have to compare xq f with xn, will filter xn with the same filter so that we can get xf, basically filtered sequence of fn, and basically we can compare this with xn, so that if xn is very low frequency signal, then this x of fn, so basically xn filtered, will be equal to x of fq, and then the mean squared error between xn and xq must be basically larger than mean squared error between x q filtered and X infilter. So we also saw that the bandwidth of the brick wall filter was pi by 10. And the mean squared value of the noise would go down by a factor of 10 because the noise is spread broadbandly over a range of pi. So if the conserved bandwidth is only pi by 10, then the density of noise will only be delta square by 12 times 10. So basically it will go down by 10. So we saw this. So what we are talking about is basically oversampling plus low pass filtering the results uh, of the quantizer, which will basically result in a smaller mean squared value of noise. So basically, we are concerned in signal to noise ratio, right? So anyway, we have to increase the signal to noise ratio. So we have a signal which is fixed. So our focus is on reducing the noise in order to increase the signal to noise ratio. So let's say for a brick wall low pass filter. So let's say the low pass filter is a brick wall. So what do I mean by brick wall? So it's an ideal filter with a steep slope. So ideally it is not possible for, but as of now, let's take for a brick wall low pass filter. We have a quantizer, then we have a filter. So after quantizer, we have a filter, and we did oversampling over here. So we will downsample by a factor of m. So why will we down factor? So our signal, so basically our signal is anyway at lower frequencies, or it's hovering around DC, let's say. So even though after low pass filtering, we have this much bins or this much frequency range or bandwidth. So even like at this point, even though if we downsample, our signal is not harmed. I mean, our signal is untouched. So it doesn't like matter if we downsample, but for our further convenience, I mean, for our further design, we downsample it by a factor of m. So basically, the whole system seems like a quantizer with a quantizing noise valued, which is delta square by 12 divided by m, if we are downsampling by a factor of m. So then quantization is done with a sampling frequency, which is fs. So after quantization also, the sampling frequency will be fs. After low pass filtering also it will be fs. But after then, when we downsample it, the frequency becomes fs by m. So if we have this whole system and we need to find the resolution of this whole system, we would just simply put a sine wave, measure the mean squared error, and equate it to delta squared by 12, and then delta value will give us the resolution of the quantizer. So this digital filter, low pass filter, followed by a dropping of samples is called decimation filter. And to design a decimation filter with very sharp roll-off, I mean with very sharp steep curve, we need to have a lot of let's say like this is the concept of digital design. So it's basically taps and holds, so taps and delays. So basically we need to have a lot of taps in the FIR filter, and having a lot of taps means having a lot of multipliers, and power consumption for digital FIR is directly proportional to number of gates multiplied by the rate of operation, which is basically Fs. So after designing a filter for, let's say, Fs sampling frequency, if we say that we only need one sample in m samples, because we are downsampling it with m samples, right? So we say after designing a filter for a frequency Fs, we downsample it by m, by a factor of m. So we say that we only need one sample within a range of m samples. Then basically the designer for the digital filter will be pissed off, because we made him compute for all samples, and now we are saying that drop all the other m minus 1 samples because we are only interested in one sample within m range. So basically the thing is, the efficient way of doing is combining the operation of decimation and low pass filtering, and together we can go forward with the decimation filter. So this is the idea behind it. So then let's talk about OSR more. So let's talk about this thing. Let's take the decimation filter further. So if FB is the signal bandwidth, so we have an input signal, and let's say FB is the bandwidth or the frequency of the input signal. So then the Nyquist rate will be simply either 2FB or greater than 2FB. So let's say the actual sampling frequency is Fs. So Fs divided by the Nyquist rate, which is basically 2FB, is called oversampling ratio or OSR. Hence, the digital filter will ideally have a cutoff rate responding to. So basically, the noise is spread over a range of pi, which corresponds to Fs by 2. So we have Fs by 2 over here, and we know Fs by 2 corresponds to pi, and the signal corresponds to Fb, and Fb then comes out to be pi by OSR, because if this FB goes here, OSR comes here, and Fs by 2 corresponds to pi. So FB corresponds to pi by OSR. So basically, the decimation filter response would look like this, where if we say it is a brick wall, then we need the bandwidth to be pi by OSR. So while designing a decimation filter, we have the specifications of the OSR. So basically, we design it for a bandwidth which is pi by OSR. And of course, when we build the decimation filter practically, no brick wall kind of response can be realized because that's ideal. Then we worry about what order of filter we need. I mean, that's the another point to be considered. But as of now, the bandwidth should be pi by OSR, or cutoff should be pi by OSR. So after decimation filter, we get an in-band signal to noise ratio. So basically, the noise which is considered now, or the noise density, remains about which is in band. So it is which is inside the bandwidth, and we have signal inside it at hovering around DC, or let's say at lower frequencies. So we have a in band SQNR, which is signal to quantized noise ratio. So now the thing is, if we double the OSR, what would happen to our in band quantization noise? So basically, we have a quantization noise in in band, and OSR is related by the bandwidth of the band, which is pi by OSR. So the question is, if we double the OSR, what would basically happen to our in-band quantization noise? So basically, we have same signal bandwidth, FB. So we have signal which is same. So FB is same. And if we double the OSR, which means our sampling frequency or sampling rate has doubled. And what happens to the in-band SQNR if Fs has doubled, or basically what will happen to the mean squared value of the noise after low pass filter? So the thing is, if OSR doubles, then pi by 2 OSR comes to this value instead of this. So now, first we are concerned within this band. Now we are concerned only in this band, and the quantization noise is flat from 0 to pi, and its density is delta squared by 12 divided by pi because it's spreaded over pi. Obviously, with a range of pi by 2 OSR, the noise power will reduce by a factor of 2 with respect to the noise within the range we had when we had pi by OSR. So simply it says that if we double the OSR, then the range, basically the noise power, will reduce by a factor of 2. So like reduction in factor of 2 is basically in decibels, it is 3 dB. So the signal power remains same, but the noise goes down by 3 dB. And thus every doubling of OSR increases the signal to noise ratio by 3 dB because noise is going down by 3 dB. So obviously SQNR will go up by 3 dB. And we know if we increase the resolution of 1 bit, then the SQNR goes down by 6 dB. So doubling the OSR is simply improving the resolution of quantizer by half a bit because it's increasing the SQNR by 3 bit, right? So the resolution is being increased by half a bit. So if we basically want a 6-bit quantizer look like a 10-bit quantizer, so we should increase the OSR by the factor of 2 to the power 8 because from like going from 6-bit to 10-bit. So every increase in 3 dB or a factor of 2, every factor of 2, we will get 0.5 increment. So we need 8 such increments. So we need 2 8 times. So basically 2 to the power 8, which is 256. So basically if we want a 6-bit quantizer look like a 10-bit quantizer, we should increase the OSR by a factor of 256. So then, now naturally we think that we are getting half bit of increment in the resolution for every doubling. So is it possible to get more out of it? I mean, is it possible to get, I mean, doing oversampling is a tough task within itself. Then if just for the doubling of like doubling, just only doubling the oversampling, we are only getting increment in half bit resolution. So is it possible to get more resolution, more than half bit by doubling the OSR? So, I mean, naturally we can think for it, right? So based on analog circuit design, so now here comes few concepts of analog circuit design. So based on it, we know that if we add some noise to the output of a negative feedback op amp, so basically we have a negative feedback op amp, and if we not like we if we add a noise to the output, uh, and the gain basically is A for that negative feedback op amp, and we are adding a noise to the output of that op amp, so the V out will be V in times A upon 1 plus A plus the noise divided by 1 plus A. And here we can see the denominator is same because the transfer function is same, because the denominator represents the transfer function. So it is the same. So if we think of this as a quantizer, so basically what is a quantizer? It's a source along with the noise, right? So we have source along with the noise, but if we talk in terms of like if we talk this in the terms based on analog circuit design, so by interpreting quantizer as an additive noise source with the input signal, if we think of a quantizer in such a way, then the noise basically don't come through the output at all over here. Why doesn't it come through the output? Because the negative feedback loop is doing its job to keep the V out equals to V in, and clearly as like the gain tends to infinity, V out tends to V in, and noise is completely gone away. So this is the concept of analog circuit design and realizing the quantizer based on those facts. So then we should bear this in mind that any physical quantizer we will try to build will have some kind of non-zero delay. So there will be some delay. So what does it means is, if an input to be quantized was given at an instance, let's say at a clock tick n. So if we have an input at a clock tick of n, so we are dealing samples, right? We are not dealing with a continuous signal. So we are dealing with the samples. So the time will be in discrete increments. So if at a rising edge of n, if we give an input to the quantizer, the output will be produced with a delay which is somewhere between nth and n plus 1th clock cycle. But if we are dealing like when we are dealing with samples and not continuous signal, so we will only see the produced output at the rising edge of n plus 1th cycle, because nth cycle is gone now due to the delay. So now we are dealing with samples. We are not in continuous domain. So anyway, we'll see the output at the rising edge of n plus 1th cycle, right? So this means there is a delay of 1 clock cycle associated with the output of the quantizer. So this needs to be understood, because when we are designing the loop now, so what we are basically doing is we are realizing quantizer as a source with the additive noise source. So basically we have a source, we have quantizer over here based on this concept. So then we also need to introduce a delay, because why? We saw it over here. And if we replace the quantizer by an additive noise source, let's say E of n, then it will somewhat look like this, where we have an input with a noise source E of n, we have output which is V of n, and we have a delay which is obviously in Z transform by. So we need to calculate V of m in terms of two input sources, which is U of n and E of n, and we have Z inverse. It makes sense to work with Z transforms over here. So basically, when we talk about the transfer function, so like this is basic like electronic circuit design knowledge. So we have U of Z, we have U of Z minus Z inverse times V of Z times the complete gain plus E of Z equals to the output V of Z. So this comes from like Kirchhoff laws, um, current and voltage laws. So when we solve this equation, so our output or V of Z comes out to be A upon 1 plus AZ inverse times UZ plus 1 upon 1 plus AZ inverse times EZ. And we can simply say that this is a signal transfer function for UZ as input with respect to output, and this is a noise transfer function for EZ as an input, and the denominators are same. So it is again, I mean, this is the same as we designed the filters. So we have a transfer function. So it shows us the transient response of, like, I mean, the transfer function of the system. So basically it is the same, but it is with respect to the, this is respect to the signal and this is respect to the noise, because we have two sources, signal source and noise source. So we have a signal transfer function and we have a noise transfer function. So basically, when we talk about a signal transfer function, so we consider this. So over here, as A tends to infinity, UZ will tend to Z, and this means the output comes before the input. So this is not possible, right? I mean, output cannot come before the input. I mean, this sounds wrong, and this means there is something seriously wrong with assuming A tending to infinity. So we will talk about this in great detail in next video. And from my side, let's stop here at this transfer function. So you guys know how to derive a transfer function. So go through it, try to realize this transfer function and try to realize the signal transfer function as well as noise transfer function. So that's all from my side for this video. Thank you so much. So if you have doubts, please let me know.